Okay, I think that's enough time. Anyone? Okay. Okay, should I go over this? Everyone seems so doom and gloom. All right. So this is implicit differentiation. So what was your question? Did you have a question? I have a review for the exam, yes. All right, so implicit differentiation, what we're going to do is take the derivative on both sides of this equation, and we're differentiating with respect to x. So that sometimes gets lost in when we actually mechanically start doing it. But what you want to remember is that we are taking the derivative of this with respect to x. And the importance of this is that when we take the derivative of x, we get 1, right? Right. And when we take the derivative of anything else, like y, we don't get 1, we get y prime. Yes? Okay, so let's go ahead and go through this. We have the derivative of 5y, so the 5 is just going to come for the ride, yes? And then derivative of y, we're just going to call that y prime, all right? So 5y prime. And then plus, now this is where things get a little bit messy. We have x times y, right? So this is a product. That's a product occurring right there. And because it's a product, we have to treat it with the product rule. And so if we label it, we could call this like our little f function, then times our g function. So now we have to apply the rule. And the rule is, you know, if you have multiplication, the derivative is f prime g plus g prime f, right? That's our product rule. So we go about this one at a time. We first start with taking the derivative of x, which is 1, because again, we're differentiating with respect to x. So this is going to be 1 times y, so no derivative, right? That's what this says, so just y. And then plus, according to the formula, plus. And then g prime, which is derivative of this, what's derivative of y? Y prime. And then we're not done, times f, and that means times x. Okay, so that's finishing off that product rule in the middle. And then we keep moving. The derivative of a constant is 0. Right? So I don't need to put that, but I will. Mine is 0. And then equals the derivative of the other side, which is still the derivative of a constant, which is still 0. Yes? Okay, let's just kind of clean it up a little bit, because 1 times y is really just y. So 5y prime plus y prime x equals 0. Can anybody explain to me what the next goal would be? Get y prime by itself, right? Get y prime by itself. And so we have a y prime in this term. We have a y prime in this term. So I'm going to get the y that doesn't have a y prime. I'm going to move it to the other side. And that means subtract it on both sides. And when I do that, I'll be left with the 5y prime that was here. I'll be left with this right here, plus y prime x. And then equals what? Negative y, because it moved to the other side. Now the whole idea of getting the y primes together and everything that doesn't have y prime to the other side is because now you can factor. I heard someone say that. We're going to factor the y prime out. Both of these contain y prime, so we factor it. So y prime comes out. What are we left with? 5 plus x. So you have to be careful here, because this times this should give you that, and this times this should give you that. It's just like factoring out a number, but we're factoring out y prime. And then negative y. Now what? Trying to get y prime by itself. We're almost there. Divide. Yep. And we divide because this is multiplication. So to undo the multiplication, we divide through by 5 plus x. And then we divide this side by 5 plus x. This cancels. We have our y prime by itself equals this side negative y over 5 plus x. Not done, right? Not done. Because now what we need to do is figure out what this derivative is at this particular point. So this is giving us an x coordinate and a y coordinate, isn't it? So we just need to come over here and replace this x with -1 and replace that y with +1. So y prime will become -1, right? Over 5 plus -1. And what's that equal to here? -1 over 4? -1/4. Does that help at all? I mean, yeah. You got what?
No, like up to that first step, and I lost it.
Right here? Yeah.
I was like, is the y now a y prime? That middle y? I got
This one right here?
Yeah.
Yeah. Yeah, it's not. You see why it's not? It's from the formula. You're doing a product rule on this, right? The product rule says that you should take the derivative of this first, which is 1, and then times this, but not with a derivative. See that g does not have a derivative. So that y, you don't take its derivative.
Yeah, I was thinking because it's just a y, like, if I do the derivative, like if I would make it a number, like if I would do the derivative.
You do y prime on the next piece, so you do plus, and then you do the derivative of the g. There's your y prime, and then you don't touch the x. Yeah. Okay. All right. Well, look. I mean, this is just a quiz, and like I said, if you didn't do well, you can talk to me after class. But you have a test on this on Monday, right? Today's Wednesday. Yeah. So you have a test on Monday on this material, so you'll have at least the weekend. So bad news is, well, if you didn't do well, you didn't do well. Good news is that we're going to do more of this today. And then there's a review, all right, so you can have something to practice. All right, so we're continuing with implicit differentiation. And I'm nervous.
What did you say, sir?
I'm nervous. We're continuing with implicit differentiation, and I am nervous for you. I'm nervous because I'm about to throw a twist into this. Okay? So let's go back to the problem again that I just gave you for this quiz. I asked you for y prime, didn't I? Okay, so I said find y prime. And it is understood when I write y prime that what I mean is for you to find dy dx. This is the alternative notation, Leibniz notation for the same thing. These mean exactly the same thing, right? And I said it was very important for us to understand that the derivative of x would be 1 because we're differentiating with respect to x. You always look at this variable right here, and that tells you which variable is going to go to 1 when you take its derivative. Okay? So when we take derivative of y, it does not go to 1, but when we take derivative of x, it does. Yes? Okay. So this is not what I want to do right now. Okay? What I want to do instead is I want to find x prime. Now, what does this mean? This doesn't mean dy dx. This means dx dy. It's flipped over. And so now what I'm telling you is that when you see the derivative of y, it's going to be what? 1. But when you see the derivative of x, it's going to be x prime. Everything just got reversed because the notation is different. Do you see that? So from here on out, I'm going to start using this notation instead because I hope that it will help you identify which variable is going to go to 1 and which one will not. Does that make sense why I'd want to use that instead? Okay, so let's go back to this problem and let's find dx dy instead of dy dx. And then we'll talk about what's the difference between the two. Like, what is this one doing and what is this one doing? Are the answers the same? Let's see. All right, here we go. Starting back here, I take the derivative 5 times something, right? That's going to come for the ride? So we get 5. Now, what is the derivative of y? 1 this time, right? 1. So 5 times 1. Plus, now, do we still have a product here? Absolutely. So we still have to do the product rule. So there's still f here, there's still g here. So now we're going to do f prime, so derivative of the first one, times the second one, plus, do y'all want me to write it up here, or y'all, no, you're okay? Yeah, okay, all right. F prime, product rule, f prime g plus g prime f. All right, I would just memorize that by now because you need it a lot. All right, so we're going to take the derivative of the first one. So what is the derivative of x? X prime, right? X prime? It's not 1 this time. It's x prime. So I can write x prime, right? Or I can write this. These mean the same exact thing, right? I'm going to write this instead of this. So the derivative of x is dx dy. Please, again, understand that this really is x prime, right?
On the test, is it going to be written that way, or both?
Is what going to be what?
Test, how is it going to be written? Both ways, or is it just going to be written like that?
Well, I'm going to give you this and ask for this. So you can do it either way, but just stay tuned. Because I think you're going to want to do this after I get to the next thing. I'm going to throw another twist in, all right? I'm not doing it, okay? You'll have to understand, I'm the messenger here, okay? Calculus is doing this to you. I'm just here to share it with you. No, that doesn't help. Okay, so that's, we just did this right here, right? That's it? Okay, then I need to multiply times g. What's g for us? Just y, right? So times y. No derivative, right? Then we say plus, now the derivative of g. So the derivative of g is the derivative of y. What's the derivative of y? 1 this time. Why is the derivative of y 1? Because we're taking the derivative of y with respect to y, aren't we? And isn't dy over dy 1? Does it make sense that that would be 1? But, okay. So derivative of y is 1 this time. Now, times what? X. All right, now we're done with product rule, so we continue. Derivative of that is 0 equals derivative of that 0, so we just get that. Let me clean it up. 5 plus dx dy times y plus x equals 0. So all I did here was, 1 times x is x, 5 times 1 is 5. I just left this alone. And I'm trying to find this, right? So I'm going to get this by itself. I want to get this by itself. And right now I have this term right there. That's where it is, right? That's where this is. So let's get everything else to the other side. Let me erase this. What should my next line read if I'm going to move everything to the other side? dx dy times y equals negative 5 minus x. You could also have written negative x minus 5. It's the same thing. And I believe we have one more step. Over y, right? Divide both sides by y. So dx dy equals negative 5 minus x over y. And so that is dx dy. Is that the same answer as dy dx? That was not the same answer, was it? So these mean two different things, right? So I'd like for us to but I need to make sure you understand what's going on here. Like, what is the difference between dy dx versus dx dy. All right. So yes,
Where did you get the -5?
right here on this point, at this point right here, I wanted to get this by itself, so I had to move the 5 to the other side. So I subtracted 5 on both sides of the equation. So when I subtract it here, it's gone, but when I subtract it here, it becomes a -5. And then the same thing with the x. I subtract x here, subtract x there, it becomes negative on the other side. Yes?
Okay.
Okay. All right, so what do these two things mean? I'm about to tell you what they mean, all right? This is saying, how much does y change by? So remember, these are graphs, right? We have a graph. This is saying, how much does y change by if I change x by just a little bit? So if I change my x coordinate, how much does my y change, go up and down? Does that kind of make sense? This one is the opposite. It's saying, how much does the x change by if I just move my y a little bit? And these two quantities are obviously different things because we have different formulas, don't we? Yes. Okay, so here, a small change in x has what impact on y? Here, a small change in y has what impact on x? Now, that may not seem like it really matters until we now throw the next layer into this. Y'all ready for the next layer? The looks on your faces makes me think not, but okay, we're going to do the same equation, right? There it is. I've already asked you what dy dx is, right? I've already asked you what dx dy is. What possibly more could I ask you?
Oh, wait. I'm sorry, we're talking about Christmas.
I know, that's why I'm pointing at you. You should be thinking about this, not Christmas. D what?
DDXY?
DD?
I don't know what other combination it could be.
Yeah, I mean, what else could I do? If these are flipped, right?
Multiply them together.
Like I could flip them.
Multiply them together?
3s? 38 over d.
I'm not expecting for you to have the answer to this. I'm expecting that you're sitting there going, what else could he ask me, right? I mean, this looks like the only combinations I could ask. The y over the x or the x over the y, right?
Wait, what if you take out?
And then you don't have anything. So here's what I'm going to ask you. You ready? I'm going to ask you how much the y changes if I just change a little bit of the t. Yeah, so you're sitting there going, where the hell's t, right? Like t's not in here, right? But t here is going to be some other variable. In most of the time, t for us is time. So imagine that you've got, normally we look at a graph of a function, right? We say, oh, okay, here's a graph, right? There it is. But what if what's happening is that, you've got this point here. It has an x coordinate and a y coordinate, like that. And maybe that's your x and y coordinate for, we can think about this as like cost or something, cost. Maybe if you have 10 employees, your cost is this, right? But maybe in the background of all that, that was in the first year of your company's business. Maybe a year later, you have a different x and a different y coordinate. So like it's almost like in the background there's a clock running. Yeah? So you have this other variable, time. I mean, think about it this way. Right now, I'm standing here, right? I have like a position of where I am in the room. Yes? You can almost look at it like an x and a y coordinate of where I am, right? Okay, let's start a clock. So there's a clock running. Initially, when I started that clock at 0, I was here, right? Okay, now, let's say 1 second later, I'm here, right? I have a different x and y, but time is also different, right? So now I step back here. So I'm back where I started, right? But time is different. I'm now at a different time. So when you have these functions like cost functions, revenue functions, profit functions, you can always think about time as being like a background variable. So sometimes we want to know how's my y changing with respect to time, even though time isn't here? All right? You're just going to have to kind of go with me on this for a minute? Yes? So, let's see if you can really pick this up. Do you remember what this I said? If we ever take the derivative of x, it's going to be 1. But if I take derivative of y, it won't be, right? Here I said if I take derivative of y, it's going to be 1. But if I take derivative of x, it won't be, right? Here, if I take the derivative of t, it'll be 1. But otherwise, it won't, right? But there aren't any t's here. So let's just see how this is going to work. Take derivative of 5 times something. The 5 is going to come for the ride. Now, what is the derivative of y with respect to t? Did you say y prime? Yes, it's not 1 though, right? And instead of writing y prime, I'm going to write this. Right? Isn't that dy dt? This is dy dt. Then I say plus, and now I have my product rule right there. Okay, this is the one that's tricky. What is the, if I'm doing the product rule, what is the derivative of x with respect to time? It's just, you almost want to say x prime, right? It's not 1 though, right? So instead of saying x prime, I'm going to write dx over dt. It's the rate at which x is changing with respect to time. What's the next part of the product rule? This part, right? So that's just going to be times y. And then I have plus. Now, what is the derivative of y with respect to time, or to t? dy dt again, right? Times the f, and what's f for us here? X, right? No derivative. And then derivative of that 0 equals derivative of that 0, so we get this. I guess what I'm telling you is that none of these derivatives went to 1. And the reason they didn't go to 1 is because the variable I was using down here doesn't appear here. So every single time I take a derivative of one of these, it's going to be one of these expressions.
Which prime do you put by itself?
Okay, so I asked, I didn't put here find. I didn't, right? I said find this. Sorry. I should have put that to begin with. Find that, okay? So do y'all see that in there? Do you see dy dt? Yeah. And it actually appears twice. It appears here, and it appears here, doesn't it? So what do you think I'm going to have to do with that thing that doesn't have dy dt in it? Move it to the other side. This entire ugly expression has got to go to the other side. So here's where we are. 5 dy dt plus dy dt times x equals negative dx dt times y. So I just took this, moved it to the other side so it became negative. And what will I do here? If I want to try and get dy dt by itself and it's here and here, what can I do? Factor it out. Factor it out. Just like we did before. It's almost like this is like a y prime, y prime. We're just going to pull that out.
So the y doesn't change negative?
Because it's multiplication, you don't change the signs of both. Because then it would become positive. I don't know who said that. I heard it. Oh, right. So it's just one factor. This is a factor, so when you move the whole factor over, it just changes signs. All right, let's factor out that, we're factoring this out of both of those. So I'm going to pull a dy dt out. And in parentheses, what will I have? 5 plus x. And then the other side is still negative dx dt times y. One final step. Divide by 5 plus x, right? This looks ugly. I understand that, okay? There it is. That's the answer. Now on your homework, you were given an equation. You were asked to find y prime. And they gave you a point, right? And then you used that point and you actually calculated some number at the end. Right? They gave you an x and a y coordinate? Okay. With this particular problem, me asking you for this, in order to find out the rate at which y changes with respect to time, you actually have to know what x is, you have to know what y is, but you also have to know the rate at which x changes with respect to time. So you'll see that when we get to an actual, like the next problem, how we need to know a lot of information. And then we're going to turn this into a word problem at some point, hopefully. We'll see. Like I said, I'm a little concerned right now. How does it feel to you? Pretty bad? Yes, pretty bad? Implicit differentiation is not a simple thing to pick up on. Usually takes a little while. All right, so maybe we should try something else. Try another one. Oops, that's a typo. So here's an example. Let C equal 400 plus 5x. So this is almost like a cost function, all right? I'm not giving you any information like dollars or anything, just we're trying to prepare ourselves for a cost function in maybe the next example. I would like for us on this to find the following. Part A, find dc dx. I would like for us to find dx dc. And then I'd also like for us to find dc dt. So let's talk about part A. In part A, if I ever see what variable, the derivative of it will be 1. X, right? If I'm ever taking the derivative of x, it's going to be 1. For part B, if I ever see the variable c, the derivative of that's going to be 1, right? Here, if I ever see the variable t, the derivative will be 1, right? But t's not up here, so we know we're going to have some stuff to deal with here, right? So let's start with part A. Okay, so for part A, I take the derivative of this equation. I start on the left-hand side. What is the derivative of c with respect to x? C prime, which I'm actually going to write dc dx, right? I'm taking the derivative with respect to x, so when I take derivative of c with respect to x, I get dc dx. No?
We don't
Are
have
you-
to. We could write just C prime. But
I wouldn't because of where we're going with this. That's what I'm trying to get you to. Last class we used y prime because it was convenient and we didn't have any special cases happening. Now we have some special cases and the notation is much better. I know it doesn't look better, but it's much better because look, this tells you what your variable is that you're differentiating with respect to. Without that, you don't know what that variable is. Let me keep going. I'm hoping that this is going to be like a light bulb that clicks for some of you at some point. What is the derivative of 400? 0. Okay, so I don't need that. Now I have plus 5 times something, right? So the 5 will come along. Now, what is the derivative of x if I'm trying to find dc dx? 1, right? Because this right here tells me that the derivative of any x I see is going to be 1. So that's going to be 5 times 1, right? So what do we have here? What is this saying? It's saying dc dt, or dx, sorry, is equal to 5. Isn't that what we were trying to find? dc dx? It's 5. Okay, that's what it is. It's constant. Let's try the next one. Let's just see if this starts to flow at all. All right, in the next problem, I'm differentiating with respect to what variable? C. That means if I see a C, if I see a C, and I take its derivative, it will be 1. Anything else, it'll be d, whatever that variable is, over dc. So let's start on the left-hand side. What is the derivative of c with respect to c? 1. Equals, now, derivative of 400? 0. And then I have a 5 attached to the x, right? Now, what is the derivative of x with respect to c? X prime, but not x prime. dx dc. dx dc. And what am I trying to solve for here? I want a dx dc, right? There it is. So I need it by itself. So why do we get rid of that 5? How do we do it? Just divide both sides by 5? So 1/5 is dx dc. Can you all see how, like, in these two problems, the derivative kind of changed places? Like here, the derivative was dc dx, but here it was 1. Here it was 1, but here it's dx dc. And it all has to do with what this variable is right here. Now the last one, we're differentiating with respect to t. And t does not appear anywhere in my equation, right? So what is the derivative of c with respect to t? dc dt. dc dt. dc dt equals derivative of 400? 0. Then we have a 5 that comes for the ride. And what is the derivative of x with respect to t? dx dt. dx dt. Are you getting this, sir?
Me?
Yes.
Parts.
Okay. Because usually you're usually getting it. So if you're off, I'm concerned.
Yeah, I'm also under the weather, so.
Okay. All right, never mind. You got it then. Well, what are they asking us for? dc dt. You have dc dt by itself, so this is the answer. Now I know it's ugly to have that there. Like this was a number, right? 1/5. This was 5. This one is saying, look, in order for me to know dc dt, it's going to be 5 times dx dt. So in the problem, as we're going to do here, I'm going to have to provide you with what this is. All right? All we're doing right now is practicing the mechanical part that we need for the word problem, and that's the implicit differentiation. All right, I'm going to give you one to work on, and I think I'm going to walk around because I get this really, really bad feeling that most of you are lost. All right, here we go. Let's try. I'll just make it up. How about we do this? Revenue equals $50 x minus, all right, let's go plus x squared. Oh man, this is going to be a disaster. All right, dr dx, I want that. And then I want dx dr, capital R. And then finally I want dr dt. All right, you think you can work on that? See what happens? Lantern A, yeah. This one's a little off here. And this one, where is it? Here. This one's a little off. I'm going to talk about this. This right here, this part right here, and this part right here is I think the trickiest part. Okay, I think you've suffered enough.
And then put 5 plus 2. And then you divide by 50 plus.
All right, let's go through this. I think a lot of you are having the same issue on part B that I expected you to have, all right? So let's get through the first one. Here on the first one, we're differentiating with respect to x, right? That means anytime we see an x and we take its derivative, it'll be 1, yes? All right, so let's start this out. Take derivative of r. What's the derivative of r with respect to x? dr dx. Okay, and it's good that we see that because that's what we're looking for, right? Okay, equals. Now 50 comes for the ride. And now what is the derivative of x? 1, because we're differentiating with respect to x. So I put times 1. Plus, now here's the part that can start to get a little bit tricky. You're asking what is the derivative of x squared with respect to x, right? So this goes back to what we've been doing this whole class. The derivative of x squared is 2x, right? Just 2x. Because we're differentiating with respect to x. So the answer is just 2x. So your answer is 50 plus 2x. And we're done. Okay? Now, the second one. This time we're differentiating with respect to r. That means if we ever take the derivative of r, it'll be 1. Otherwise, it's not 1, right? So what is the derivative of r with respect to r? 1, I just said that, right? Equals, now 50 comes for the ride, times, what is the derivative of x with respect to r? dx dr. All right. I think most of you are good up to that point. This next part is the part that's tricky. And let me just remind you, do you remember the chain rule? You had some homework like this, where you were asked to take the derivative of something like this. And so what you did to take its derivative is you brought the 6 out, you rewrote the 3x plus 4, but you didn't touch it, right? You reduced the power up there to 5, and then you said times the derivative of what's in here, yes? Which would be 3 here, right? You remember doing that? So the idea behind this is, let's just look at it this way. Maybe I can break it down like this. If I have this dirty, nasty cloth, right, raised to the 6th power, the derivative of a dirty, nasty cloth is 6 times the dirty, nasty cloth, right, to the 5th power. Times what, though? The derivative of that dirty, nasty cloth. So you always have to go back in and take the derivative of this, yes? Okay, so right here, when I'm looking at, I've got 50 and then the x, we got that, then plus. Now I'm coming to take the derivative of x squared, which should be 2x if we're differentiating with respect to x. But because we're not differentiating with respect to x, it's more than just 2x. Now watch. So I treat it like this. First, it's like I have my dirty cloth squared, yes? What's the derivative of my dirty cloth squared? 2 times my dirty cloth, which was x, to the 1st power, yes? Times, now, the derivative of what's in here, right? So what is the actual derivative of what's in there? What's the derivative of x with respect to r? dx dr. And that gets slapped on to the end of this. That's the tricky part. The fact that this thing pops out. When you take derivative of x squared, normally you're like, 2x. But when you're differentiating with respect to capital R, you get this dx dr that pops out because of the chain rule. All right, let's try this last one. All right, so for here, Oh, sorry, yeah, you're supposed to solve for dx dr. Yeah, so you have to factor, sorry. So both of these have dx dr, right? So you can factor it out. When you factor it out, you get 50 plus 2x. Right? So I'm factoring this one and this one out, and that leaves me with a 50 and the 2x and a plus between them. And then I divide both sides by that. So I'll divide this side by that side by that. So 1 over 50 plus 2x equals dx dr. That's the answer. Let's do this last one. This time I'm differentiating with respect to t, right? And since there aren't any t's anywhere to be seen, I'm never going to have something go to 1, right? Ever. So let's start. What's derivative of r with respect to t? dr dt equals 50 times dx dt, drum roll, plus 2x dx dt, dx dt, because remember we're differentiating with respect to t. So this 2x dx dt comes from that chain rule again. You have to bring the 2 down, x to the first power, and then the derivative of x with respect to t, which gives you the dx dt.
That's it.
Well, we're supposed to solve for what? dr dt? So yeah, it's already solved for dr dt. So that's it.
We couldn't do it how we did it. How we put dx over dt times 50 plus 2x.
Well, we're supposed to find what dr dt is, right? That means get it by itself. Well, it's already by itself. You see?
Simplifies the right side.
Oh yeah, you could have factored that. Yeah, that wouldn't have been wrong. You just leave it like that. All right, well, we have 10 minutes and
How many of these do you expect on the test?
well, I mean, we didn't really even get to where I wanted to get. I have 10 minutes. Let's try one more thing here. Let r be equal to 10x minus 0.5 x squared. Find dr dt if dx dt equals negative 40 and x equals 2. All right, so this is pretty much like a problem you would see on the test right here. But I'm really, really hesitant at this point. I mean, it's supposed to be. We're supposed to actually be in the next section already, but we are bogged down.
Well, I mean,
You know.
I'm not gonna lie, but we spent the last 15 minutes on the class, and then we had a quiz on it, and I don't think we had a full grasp of this class. Maybe
I understand that.
time.
This is a difficult topic. Otherwise, I mean, what I'm saying is I'm not quite sure I'm ready to put this on the test, you know? Because I know y'all wouldn't thumbs up that, you wouldn't say, yeah, that's great, but then your next test is going to have that much more stuff on it, you know? So, you know. Okay, let's Let's work through this. I want to know what dr dt is, right? If dx dt is negative 40 and x is 2. So first, let's figure out what dr dt is. You all agree? We can do that first? So we're differentiating with respect to what variable here? T, and that means that nothing is going to go away to 1, right? Everything's going to be d something dt, d something dt. So let's do it. Derivative of this, dr dt, equals, all right, 10 times dx dt. That's a derivative of x with respect to t. Okay, minus 0.5 comes for the ride. And now I need to take derivative of x squared with respect to t. Times 2x. I'm going to write like this. 2, that's my 2. X
Times dx.
times d what?
dr.
dx dt. So here's my 2x, right? That 2x you get from taking derivative of this. But then this is the part that you get by the chain rule by taking the derivative of x. It's dx dt, not 1. Okay, so that's what dr dt is, right? Now, I want to know what this is if I then tell you that dx dt is negative 40 and x is 2. Just plug them in, right? Like, that means you're going to replace this and this with negative 40, right? And you're going to replace this with 2. And you're going to get an actual numerical answer here. dr dt equals 10 times negative 40. That goes there. And then what are these two numbers together? That's a 1, right? Half of 2 is 1. So you get minus, that's this, x, which is 2, and then dx dt, which is negative 40. So when we put all this together, this is negative 400. And then these two together be plus 80. Negative 320.
How'd you get -2?
Because it was up there.
Negative 2.
-2.
Wait a minute, hold on. Too many. How did I get negative 2? Well, that was a minus, right? Okay, so this right here, these two together, that's half of 2, which is 1, right? And then this x right here is 2, right? It's this x right here that's 2.
We could just skip that whole middle section, right? Just start plugging in.
Skip what middle section?
Yeah, the dx over dt. No, the one up. We could, no, that one. Do that middle one.
How are you going to skip this section?
Well, because we already have like all the inputs, right? So we could just input all those to the equation already.
I guess I'm not. You can't skip getting this. Like you have to actually get this, right?
Yeah.
But then you just plug them in, and yeah, you don't have to show all this work. I mean, as long as you plug them in and get this, you're good. But you still have to figure out what this derivative is. All right. Let me hand this out.
Yeah.
All right, we are still going to have a test Monday. That's not going to change because we do need to get that grade in. But let's talk about what's going to be on it. There should be enough there for everyone. All right. So you're going to have to reference some of your notes for this stuff if you don't remember it. For the first problem, use basic differentiation rules to find the following. So we did something like that on the last test. That was actually a problem from the last test. You have to rewrite everything as x to different powers and then take the derivative. Number 2, use the product rule to find the derivative. 3, do the quotient rule. Number 4 and 5, use the chain rule. Number 6, just look in your notes. We did a problem like that. It was when we were talking about the difference between exact cost and marginal cost. And I said, be real careful because on one of them you have to go backwards one. Does that sound at all familiar? It was when I was using that little projector thing over here. Okay, so there's 2 problems like that. And then number 8 and 9 is where you start getting into implicit differentiation.